Welcome to part 2 of the Friday the 24th flashback of January Flashback Friday work. We are beginning from question 5. In question 5 we have another transformation style question. Write down the coordinates of A which are write down the coordinates of point A which is transformed on the curve with the following equation. We start off with a mod transformation. An outside modulus transformation will cause the graph to invert all its negative locations into positive ones. So that will mean that the negative portion of the original graph will become positive. This will of course affect location A, not in its x coordinate but in its y coordinate, moving it to the point 3, 4. In part II we have a different transformation. We have a horizontal and vertical stretch. In that horizontal and vertical stretch, we're making the graph twice as wide and twice as tall. This will affect all the x and all the y coordinates, making them all essentially twice the size. I won't do the full sketch, but given that we know that both the x and the y coordinates are affected by twice the size, the A location is going to move down here to 6, -8. In part B, we have to do the sketch of the function where we now have the mod on the inside. An inside modulus transformation takes the original positive element of the curve and copies it onto the negative side. The original negative side is removed and we make an exact replica on the negative hand side, perfectly symmetrical in every way, including this point, which is not point A, but is a point equivalent to point A on the new side of -3, -4. It says on your sketch show the coordinates of all turning points and coordinates of the points which cut the y-axis. Given that I've now notified the new location on the left-hand side, minimum location, and if we just confirm that the y-intercept is 0, 5, we have now all intersections on the y-axis and turning points signified. The curve of the equation f of x is a translation of original x squared. Find the curve f of x. There are 3 aspects for us to consider here. Most people may assume 2, but there are actually 3. The original quadratic curve sits nicely on the origin, so we need to move the minimum point of on the original x squared curve that is on the origin down towards the location 3, 4. This will require a horizontal translation and a vertical translation. These are 2 transformations we can execute relatively easily. We then also, however, need to consider the scale of the quadratic to make sure the y-intercept matches up. We start by considering the horizontal and vertical transformation. A horizontal shift 3 units to the right will involve an x -3 on the inside of the function, and a vertical shift downwards of 4 will involve a -4 on the outside of the function. Remember, the original function is x squared. So this now puts my equation in the correct minimum location. Does this equation pass through the point 0, 5? Well, we could test this at x equals 0, y is equal to -3 squared minus 4, which is 9 minus 4, which is 5. So we don't have to make any further alterations to this equation to make the scale of the equation match to the correct point on the y-axis. If we did, it would have gone in here as a multiplicative scaling vertical factor in order to make sure the y-intercept reached the correct position. Question 6 is another mod functions question, and in this mod functions question we need to be able to sketch the graph, the mod of 8 minus 2x. I start off by just drawing regular 8 minus 2x. I think this is the best possible technique to use. The regular 8 minus 2x would look something along these lines, passing through, hopefully you would agree, y-intercept locations of 8 and x-intercept locations of 4. When you then apply the modulus, the negative part of the function will be removed and reflected, which I will do in a different colour, up into the positive axis area. So this is my overall sketch with my intersections included. It then says solve the equation mod of 8 minus 2x is equal to x plus 5. I think having the x plus 5 equation on here will be valuable. X plus 5 is less steep than the 2x gradient we were considering previously, which means the black line x plus 5 is going to be a less steep equation. We can clearly see this intersects in two locations. One where the modulus was not acting and we were on the original 8 minus 2x graph, and one where the modulus is acting, and so we need to include the negative that that modulus would bring. So we're going to essentially be solving two equations, one of them where the modulus is inactive and not assisting the curve in its reflecting capacity, and one where it is. And when it is reflecting, it is making all the y values negative, so we add this negative bracket around where the modulus brackets would otherwise be. Solving these two equations is then an easy matter of linear rearrangement. 3 is equal to 3x, x is equal to 1. For the first solution, we can see that does agree here. It does seem to sit approximately in the 1 position on the x-axis. And likewise, when we solve the right-hand side through rearrangement, we get x is 13, which also seems to be reasonable for the second solution on the right. The function f is defined as x squared minus 3x plus 1 between the values of 0 and 4. We need to find f of g of 5. G of x is the original function stated in the beginning of the question. To calculate f of g of 5, we should first of all just calculate g of 5. We do this by substituting 5 into the equation. The modulus sign will indeed alter the answer, giving us a response of 2. We can then do f of g of 5, but since g of 5 is 2, we can just do f of 2. So we're using one function to chain it into another. F of 2 is 2 squared minus 3 times 2 plus 1, which is 1. Minus 1 even. Finally, in part D, we're asked to calculate the range of f. The range of f is most easily done, in my opinion, with a sketch of the graph itself. Most ranges can be easily calculated with a brief sketch, especially with a graph that you should be able to sketch well. F is a quadratic, and it's a quadratic that has a minimum location rather than a maximum location. It's also only to be drawn between 0 and 4. The overall quadratic is going to look something like this, just as an approximate sketch by considering its minimum location of approximately minus 1.5. 1.5, not minus 1.5. But because we are only drawing some of this function, we don't need the graph before x is 0, and we don't need the graph after x is 4. Now, in order to work out the range, I need to work out the highest and lowest values. To do this, I'm going to need to know 3 locations. I'm going to need to know how high this location is, how high this location is, and how high this location is. Given that it's a sketch, I don't know that this is the highest point. I could have sketched it slightly incorrectly. So I'm going to calculate both of the top locations, just in case I have not sketched them the right way around for their highest values. The first location on the left is the value when x is equal to 0, which is 1. The location on the right is the value when x is equal to 4, which is 16 minus 12 plus 1, which is 5. So the point on the right is indeed the highest possible location. To find the lowest location, I clearly need to find the height of the minimum point. There's a whole variety of different techniques for this, going from completing the square to using symmetry, or just using simple differentiation. I'm going to go for the differentiation option in this case. So the differential of our function is x squared minus 2x minus 3. Giving us a stationary point where this is equal to 0, x is equal to 3 over 2. When x is equal to 3 over 2, I can substitute that into the original function, and that will give me a y-coordinate of negative 5 over 4. That makes that our lowest possible value of the function. And so our range of f of x is between the highest value I calculated, 5, and the lowest value, minus 5 over 4. Given that our range does include the value of 4, I need to be inclusive of both the 5 at the top end and the minus 5 over 4 at the bottom end. Going on to the statistics section now. In question 7, we have to work out the total number of staff who claim less than 10 hours of overtime in 1 month. To do this, first of all, we need to work out the frequency density scale, and we can do this by utilizing the information provided in the question that there are 40 staff in the whole month recorded in this whole histogram. That makes the total area of this histogram equal to 40 people. So we need to think about how we're going to make a conversion rate between those 40 people and the areas that are underneath each one of these bars. So we're going to have to calculate the area of each bar so that we can relate it to the overall total frequency. The first bar appears to be 2 wide. And if we count the major sections, we have 1, mark them on, 1, 2, 3, 4 major sections high. We could call that 40, I think, since each major section is made up of 10 smaller sections. So let's call that 40 high, just for the sake of easy counting later on, which gives this an area of 80. I don't really know what the units are, but it's an area of 80. The second bar is 3 wide and 20 high, so it has an area of 60. The third one is 5 wide, and if we count the small squares, 1, 2, 3, 4, 5, 6, 7, 6 high, which gives it an area of 30. The next one is 10 wide and 2 high, so it has an area of 20. And the last one is 10 wide and 1 high, which gives it an area of 10. The total area then here, therefore, is 80 and 20, 60, 30, and 10 is 200 units of area. 200 units of area is the equivalent of 40 members of staff. Therefore, each member of staff is represented by 200 over 40 units of area, which is 5 units of area. Now that I have a conversion rate from area to staff, I now answer the question, which is less than 10 hours of overtime. So that is the section on the left, the section in here, and the third section, the first 1, 2, and 3 sections. We've already calculated their areas, so we just need to sum those up as a fraction of the total. We've got 140 plus 30 is 170 units of area in that space, and we just need to use common ratios in order to work out how many staff that will be. Doing 170 divided by 5 gives us 34 members of staff within that space. There are a whole bunch of other calculations you can do to calculate this number. You can work out the area in terms of physical squares present, which is not quite what I've done here because I've counted the actual units using on the x-axis. But there are a number of different area calculations you can go for. They all work in a similar manner by equating ratios.